Hey everyone, we're back and we are looking at chapter 13 and we're actually going to start on chapter 13.2, which is finding the area under a curve. And the word curve used loosely just means a function. And we're going to start with an easy one. Oops. I want to go right through 0. There we go. So if I have y equals 2x, and I want to find the area underneath this from 0 to 2. So here we're at 2, and up here we're at 4, right? Well, I know this is a triangle, so I can just do 1/2 base times height. So 1/2, the base is 2, the height is 4, so that would just be 4. So this is really the answer I'm looking for. But let me turn this off, hold on. But I want to use some calculus because that was not fancy at all, and I want to be fancy. And so what I can do to estimate the area underneath a curve is to use rectangles. And I can use this rectangle here and then this rectangle. And it's kind of an estimate. And this rectangle has a width of 1 and a height of 2. So its area would be 1 times 2. And this one has a width of 1, but a height of 4. Let's see, it'd be 2 plus 4. That gives me 6. It's not right, but it's an estimate. If I have a really fancy function, if I have this and I want to find the area underneath here, well, now I could construct a whole bunch of rectangles and I could add up the area of those rectangles, and it kind of gives me an approximation of the area underneath it, right? You get the idea? So we can use rectangles. Oops, let me do this. We can use rectangles to estimate the shape that we're trying to find the area under. And that's what we're going to do here. And you can see here, I didn't do so good. But let's say we go into the middle and we go there and there. And I wish I could draw straight lines with this, but I haven't really figured out how. Now let me go to the eraser. Don't need that. Don't need that. What I do need is that. Okay, so now I've increased the number of rectangles that I'm using to estimate the area underneath this function, which I call loosely a curve. And now each one is 0.5 wide. So this one is 0.5. It does not go up to 2. It goes up to 1, because 0.5 times 2 will give me the height, 1. And this one goes up to 2. And this one, I'm at 1. 1.5 times 2 would give me 3. So this rectangle has an area of 0.5 times 1. This rectangle has a width of 0.5, but a height of 2. This one has a width of 0.5, but a height of 3. This one has a width of 0.5 and a height of 4. So this is 0.5 plus 1 plus 1.5 plus 2. So 3 plus 2 is 5. Look, we're getting even closer. I bet if we broke this up again, and used 8 rectangles instead of 4, we would get even closer to the actual answer. So as you can see, so let me draw this picture if I can. Man, that is an ugly frickin' picture. Okay, and then let me get my eraser. Get rid of the stuff I don't need. Don't need that. Did I need that? I don't really know. I don't need that. I don't need that. So now you can see, well, what happened to my, oh, wrong one. Okay. So now you can see that we don't have a whole bunch of stuff sticking out over, right? All of these little areas here are error, right? We're above the curve, but there's not as much of it because we made more rectangles. And so as the number of rectangles increases, the accuracy will increase. And if I write it another way, the width of those things, the width of the rectangle, delta x, as that goes down, the accuracy goes up. When we use more rectangles, this always causes the width to go down. And as these get really, really, really small, the rectangles start matching the function much, much better. And I want to show you this in a cool little video. Where is my video? I think I have to go here. Oh, that's interesting. Okay, so you're looking at my desktop, and then did I close it? No, I didn't. Okay, so if you watch this, somebody wrote a piece of software, and they have this curve, which looks like a y equals x squared or something. And this shows the number of rectangles they're going to use to compute the area. And this is the area of all the rectangles. This is what the actual area should be. This is the correct number. So it's going, and he's saying something, nope, 2 rectangles. You see, we're getting bigger and bigger, but the area we're calculating is higher than the actual because of all this stuff that's above the curve. We could have chosen it so we were doing rectangles below the curve, and then we would be below the actual value. Doesn't matter which way you do it. So you see the number of rectangles is getting bigger. We're getting closer to 21. And those rectangles are more closely matching the shape of the curve. And if we keep going and going and going until we hit a billion of them, then we will match it probably really, really accurately. So this is the thing we're trying to do with calculus, is we want to do this, measure the area underneath the curve with a whole bunch of rectangles. But the number of rectangles we want to use is infinity. That's really what we're trying to do. And so let's stop sharing that and go back to, oh, there was Safari. Let's go back to here. So what we want to do is, instead of adding up all these rectangles, and one way to represent add is the sigma notation. So if you have A1 plus A2 plus A3 plus all the way A to the n, you could write this as sigma A to the I, where I goes from 1 to n. So this just means add. Sigma means add. And so that's what we're doing here, is we're summing the rectangles really, we're doing height times width, height of the ith rectangle. So from I equals 1 to n. And let me get rid of, oops, sorry. Get rid of this again. edit, cut, go away, go away. So what we want to do is add up all the, did I spell height right? I don't think I did I? Oh, well. Yeah, I was never a literature guy, even though I write books. Kind of ironic, right? So we want to add up all of these rectangles to get the area under the curve. And we do it by measuring the height of the rectangle times the width. And this will give us the area. But in the limit, as delta x goes to 0 and n goes to infinity, excuse me, this function, this summation function, oh, I think that's right, the height of the ith rectangle times delta x, this ends up becoming an integral. And delta x becomes dx. And we integrate across whatever range we're doing it here, whatever the limits are for delta x. So in our case here, this would go from 0 to 2. And so this is no longer called an indefinite integral. Indefinite integrals always ended up with that plus c at the end because we didn't know that constant. Well, here we're not going to get that because we have specific limits. We're using it in a specific area, in a specific region, and so this makes this a definite integral. And there will be no integration constant anymore. So this is what we're trying to do. We're trying to integrate a function to calculate its area under the curve. And that's one of the other things that an integral does. It can be the antiderivative, but it can also tell you the area under the curve. And that's what we're going to do in this next section. And we'll go ahead and stop this here, and then we'll do some examples. Okay, bye-bye.